Hello, my name's Ffion Dunne from Imperial College in London. I'd like firstly to thank the organisers of the BSSM meeting for inviting me, giving me the opportunity to introduce to you microstructure-sensitive fraction mechanics. I'd also like to just acknowledge the many previous and current PhD students and colleagues who have contributed to this work. I'm going to first of all start with an example of microstructural sensitivity, just to show cases where it is important. I'll then briefly review some of the classical drivers of crack growth particularly, and then go on to introduce microstructurally sensitive mechanistic driver, which we utilise, which we call the stored energy density. And I'm going to look at then a number of examples and tests of that methodology to demonstrate that there's hopefully something useful to it. So the example I wanted to look at is that of zirconium alloy zircon 4, often used for cladding nuclear fuel in civil and power station energy nucleation generation. And in the middle top figure here, you can see an example of a microstructure of the cladding, and the dark streaks are effectively hydrides. These are zirconium hydride particulates, platelets, which form when the hydrogen content exceeds the saturation level. And the hydrogen is often driven by stress raises. So the hydrides shown on the right here, top right, tend to develop near stress raises, exactly where you don't want them, because they tend to be very brittle and cause nucleation of defects, which hence then subsequently grow in fatigue. So they grow also at the level, the length scale of the grains of zirconium, so clearly influenced, for example, by their orientation relationship with the zirconium. They're clearly important and are relevant to the microstructural scale. So once a crack is nucleated in this context, then they grow in the textured zirconium alloy, and the bottom figures show this now, some examples. Let me get the pointer. So in this first one on the bottom left, the crack's nucleated from a notch. The EBSD match shown on the right grows up, and then effectively it grows in a single crystal region, the sort of darker green area. And what's very interesting is that this crack oscillates, its path changes even within the single crystal. It's not that it's hitting a grain boundary and changing, it's oscillating within the grain itself. If we look at the same loading conditions, but a very different sample with a different microstructure, this time organised with the HCP hexagonal grains organised such that their C-axes are parallel with the growing crack, then the crack seems to remain largely straight and parallel with the prism planes, but growing in a direction which is therefore perpendicular to the prism plane Burger's vector. In this case here, the cracks appear to be growing parallel to the prism planes, but in parallel also with the Burger's vector. These grains, with respect to horizontal loading, are well aligned for slip, whereas these grains are less so. But the difference is that this crack grows much more slowly than this crack, in that there's a very significant difference in rate of growth, and there's also a very significant difference in the nature of the path that the crack takes, influencing the overall growth rates as well. So clearly very microstructurally sensitive. The drivers for crack growth developed in the past, the classical ones of course include Griffith, which was the balance of energy related to the new surface generation. The surface energy is given there as gamma, extended to incorporate plastic work. In parallel, the stress intensity approach, which has been used very successfully, of course, for conventional cracks and crack growth, but is very much with the limitation that the material is assumed to be elastic. In general, it's also isotropic. You've got a homogeneous medium, and the crack is growing in an infinite medium where boundaries are infinitely far removed from the crack. So a range of limitations, and in addition to which neither of them explicitly recognise a microstructure as such. So as a crack approaches a grain boundary, for example, it's difficult to see how these approaches could be generalised to incorporate the microstructural information. The one method that incorporates plasticity in any detailed way is the J integral, of course, but also suffers from the same sorts of continuum problems and the absence of representation of microstructure. And then Parasaur, of course, which is for crack growth, is related to delta K, so therefore has the same issues associated with the stress intensity. So there are a whole range of issues with these methods that don't immediately make them obvious for looking at the understanding of microstructure-sensitive crack nucleation, or particularly growth. The classical nucleation model, of course, was developed by Tanaka and Murray, and I won't dwell on the details, but just to point out that it's at the grain level. It recognises the development of localised slip along slip planes and the anisotropy, and it argues very clearly that it's the irreversible motion of desiccations which is the aspect driving fatigue crack nucleation. And this means that it's not therefore the plastic dissipation, that energy has dissipated. Therefore, it is rather difficult to see how that can be utilised as a driver for crack nucleation or growth. But of course, what Tanaka and Murray did make clear is that there is a progressive process of the development of desiccation structure where they pile up, and often there's lattice curvature associated with that, and that is a mechanism by which energy can be stored, and it's free energy because it's recoverable in the configuration or structure of the desiccations as they pile up and form within the microstructure. So this is a key issue that we've built upon in looking at desiccation methods to understand fatigue crack nucleation and growth. So I will not dwell on this either very much because I'm going to move on to higher level methods, but the overall approach is to recognise that we have stored energy elastically, which is recoverable. We also have energy associated with the desiccation structures, and those desiccation structures we can to some extent calculate and quantify the energy associated with them, but the energy is there, free energy, to drive potentially crack nucleation and growth. So in terms of the desiccations, some of that energy is just the individual line energy associated with discrete separate desiccations, so that's not relevant to us. What we're really interested in is the configurational energy, the energy associated with those desiccations which are piling up and forming structure, generally carrying lattice curvature. And we calculate that energy and go one more further step, because we're only interested in the energy that's associated with the storage over the area relevant to that over which the desiccation structure is formed. And as a consequence, we're interested in the density of geometrically necessary desiccations, and this quantity is then an energy per unit area. So just like Griffith, it's related to the driving of new surfaces. Okay, we call this the desiccation configurational energy and can calculate it from desiccation dynamics. And the argument is that we, at a crack tip, for example, where we get pile-ups, desiccation structure form, particularly curvature, then once we've developed sufficient energy per unit area, which is greater than the energy per unit area needed to generate a new surface, then the crack nucleates or grows. So that's the idea. But I'm not going to say more about the desiccation approach, although we've done quite a lot of work on that to relate it to the crystal plasticity approach, but we need to scale up to a length scale that's relevant, even hopefully to component systems and situations. So it's the same sort of methodology. We're calculating the energy stored in desiccations. So we take the fraction of plastic work that is stored, that is between 1 and 5%, and then we normalise in exactly the same way as the desiccation method with the desiccation density to make sure that this is the energy stored over an area representative of that which is storing the desiccation structure. So it's this crystal plasticity formulation I'm going to follow through from here on in. Okay, the last bit of theory I want to talk to you about, without going into the detail, is based on this stored energy density for driving new surface generation. Can we quantify the stored energy density, this microstructure-sensitive measure, in terms of classical fraction mechanics? So if we just focus in down at the bottom, there are some simplifications because I'm just using a single slip plane to simplify everything ahead of crack tip, and I'm looking at all the quantities of interest in that slip plane. And if we do that with knowledge of the geometrically necessary dislocation density, which we can get from the plastic strain gradients, which we can estimate, and from the definition of the stored energy density, which we looked at just a moment ago here, it transpires that we can obtain an analytical expression for the stored energy density. And what's quite nice about it is two things. First of all, it relates to classical fracture mechanics because the stress intensity is very definitely explicitly recognised in there. But in addition to which, it recognises microstructure because the critical resolve shear stress, or the intrinsic slip strength, in other words, which is different for differing slip systems in crystals, is also there. This of course increases with hardening. It also recognises the shear modulus in there, mu. So the other major positive about this particular approach is that this quantity is therefore finite and non-singular at crack tips. And that really differentiates it from any other measure in terms of plastic strain or dissipation or stress even, because all these quantities are singular at crack tips and also pose a great difficulty even in plastic media, elastic plastic media, because these quantities all then depend upon distance from the crack tip and the meshing and so on. So the nice thing about the stored energy density is it is not singular, it's finite, and therefore we'd expect to converge to a finite value at a given crack tip. And I'll come back to that later on. Okay, I'm now going to briefly introduce some work on single crystals where we were interested in fatigue. 3-point bend shown on the left, where we've got a single crystal of nickel, very particular and quantified crystallographic orientation, and we're subjected to loading with digital image correlation. And we see the development of these slip traces, which then grow and develop in intensity, indicating the progressive development of strain. And in this region where the slip develops, you can see on the front surface of the sample here, it's activated. Those slip traces are the very same ones you can see here. It's a single slip system activated with a very defined region of activation. We also see a region in the sort of mid region of the sample in there schematically, where we see another slip system activated, this time slip system 3, which is horizontal. It's where the shear in the beam is maximum. So we do see these two differing slip systems activated and with very defined ranges over which they are activated. And we can show with our crystal plasticity modelling of this particular loading configuration that yes, we match the slip system 10 development and its shape really quite well. And we also note the activation of slip system 3 in the mid region of the beam, reflecting what's going on there. So it gives us confidence that our crystal plasticity modelling is getting into really some of the detail going on in the crystal. The very same test then with subsequent cyclic loading leads to the development of cracks on the free surface, and that's what we can see here. You can see the slip traces to start with though, and then the crack grows. It's very crystallographic. It grows up parallel effectively to those slip traces, and there's one crack there, and there's another crack, we call it crack 2, just there, which nucleates and grows later. With our modelling then, what we find is that we can look at the plastic strain, captured by the slip of course. So there is high plastic strain in the region where that crack nucleates, shown by the red arrow. And the second crack, at this stage, there's no sign of any high strain before the crack nucleates. The stored energy density, this quantity I've just been describing, shows very high value where crack 1 nucleates. And indeed, it's the highest at any location along that free surface there of the beam, as shown by the studies here showing stored energy G with cycles. You see it evolves pretty quickly over the first few cycles and then stabilizes to evolve cycle by cycle. But these other curves indicate different locations along this free surface. And so the highest evolution is clearly this location. And interestingly, crack 2, which is over there, to begin with, there's very little stored energy. It's much lower in there. And I'll come to that in just a moment. But in general, what we find is that the cracks do seem to nucleate at locations with high stored energy, first of all, but often they coincide with regions of high slip or plastic strain as well. However, there are regions of plastic strain, high plastic strain, for which there's no fatigue cracking. And this happens many, many times in our observations in a range of material systems, indicating that plasticity is sufficient as necessary, but is not sufficient. So a necessary and sufficient quantity, we argue, potentially is the stored energy density. Just addressing this second crack briefly then, knowing that the crack nucleates here and grows, we know that that's going to lead to very significant redistribution of all the key quantities of stress, slip, stored energy. So we explicitly introduce a crack using XFEM within our crystal plasticity formulation. And of course, you get the bands of slip ahead of the crack tip, are very concentrated. But the point is, introducing the crack has therefore redistributed all the key quantities. And you can see the plastic strain much lower here now than ahead of the crack tip. And it's redistributed it over to where we do see crack 2 nucleating. The stored energy density turns out to be highest at this location. You can see there's a range of there's a fields distribution of stored energy, but it's highest at this location. And this really suggests that if we are able to nucleate a crack and we take due account of the fact that all the key quantities redistribute, we're likely also to be able to capture secondary cracking by virtue of the stored energy density. That's quite encouraging. Moving to a slightly more complicated system where we have oligocrystals, that is, these are polycrystalline structures, but they're directionally solidified. So the crystal orientation and the morphology of the grains is approximately uniform as you go out of plane direction. And we can model these with explicit crystal plasticity representations of the grain structure and the crystallographic orientations, of course. Then we cycle them in the lab, and we look at where the cracks nucleate, and then we check them against our models and the key quantities. So that's where we find the crack nucleating, where that red triangle is reflected up there. That's where we find the highest slip. That's where we find the highest stored energy density. But again, along the free surface of this sample, we've looked at the evolution of stored energy. The highest is by far and away what we see at crack 5. In other words, at this location, it's there. All the other locations within the region of interest are much lower, but they all show the same sort of characteristics. They evolve pretty quickly and then stabilize. Another example, which we call oligocrystal 3, is shown on the right. And here, a very different crystallographic structure, different microstructure, but again, we capture precisely where the crack nucleates in this case also. So, and by a very strong margin away from other regions where the stored energy density is much lower. So very clear identification of that defect nucleation. Finally then on nucleation, moving to full-scale 3-dimensional polycrystals. Again, it's a nickel alloy, it's RR1000 powder metallurgy alloy. Being a PM alloy, it sometimes incorporates these agglomerates that come from the manufacturing process, which are brittle and generate, they act as nucleators for slip-driven fatigue crack nucleation. And you can see in the experimental observations the crystallographic slip-driven fatigue cracks which have nucleated 6 cracks around this agglomerate over cycles. And this we can again represent in our modelling explicitly all the grain orientations around and morphologies, as well as the agglomerate as an elastic, a brittle medium, and we can model that at least on the free surface. And then in particular we can focus in on the perimeter of the agglomerate, which is where the cracks nucleate, unwrap this as a straight line, path DD dashed, and have a look at then, first of all, the density of geometrically necessary dislocations. And we see that those peaks of high GND density do typically coincide with the locations of the cracks, but not always. As you note, there are 1 or 2 locations where we get high GND densities, but no observation of cracks in the experiments. So again, I would argue that the GND density carries curvature, that's what it means, reflects lattice curvature, energy stored therefore, are necessary for crack nucleation, but not sufficient. If, on the other hand, we look at stored energy density, and again along that path, we see the highest values of stored energy in all cases corresponds to exactly where we see these cracks nucleate. So there's really very good overlap between high stored energy, where we see cracks nucleate, and in addition, those locations where cracks do nucleate definitely have the highest stored energies of any locations around the agglomerate. So there are other locations where there's relatively high stored energy, but it's never as high as that needed to drive the cracks in the other locations. Again, suggesting that there's a critical value of stored energy density, which is needed to be achieved in order to drive crack nucleation. Okay, so I'm going to move on to crack growth now. Back to the example of zirconium, where we saw cracks of very different character one crack oscillating within the single crystal region of this polycrystal, where the path changes even within the single crystal region. Another where the crack grows relatively straight and appearing to be parallel to the prism planes again, but again, in this case, it's normal to the Burgess vector direction, whereas here it's parallel to the Burgess vector direction. But in addition to which, the cracks growing in these two scenarios here, this grows much more rapidly than this crack. So the planes upon which this is growing are such that the cracks, for one reason or another, have a much higher rate of growth compared to this. And to some extent, it's related to the ductility, because in this orientation of the crystals, we do see an awful lot more plasticity. And so it must be related to that, and the drivers of the stored energy density, potentially local to the crack tip as it grows, will be different because of the differing microstructures. And these are the things we hope to be able to capture with our stored energy, the oscillations and also the rates of growth. So in order to address this, first of all, I'm going to look at experimental measurements where we're using a lab-based approach with a Shimadzu testing machine. This is where we do our beam, 3-point beam testing. It's a little small in there, but it's in there somewhere. This is a Questar long distance microscope, enables us to get resolution of about minimum 5 microns down within the region of interest in order to capture crack growth at the notch, and also digital image correlation maps for tracking strains and other quantities at the crack tips. And we've chosen two extreme examples for this. One is the case where, yes, the cracks are growing parallel to the prism planes in the Burgess vector direction, in other words, lots of plasticity, and this case where the cracks are growing typically parallel to the prism planes but perpendicular to the Burgess vector direction, so it's more constrained elastically. And in the experiments, first of all, what we clearly find is that there are very different rates of growth. So this is crack growth rate versus crack length. The blue symbols correspond to the this example over here, sample BY, and the red symbols correspond to this case here. So this case, enabling a little more plasticity, seems to be leading to lower crack growth rates. But as we increase crack length, so the crack growth rate increases, of course, because of the stress increase. But the rate of growth for sample BY, where the cracks grow parallel to the prisms but along the c-axis direction, is considerably higher. And we also have this very interesting region around here where we see these variations in the growth rate, and that corresponds to this region in here where the crack is growing through interesting regions of microstructure, that is, crossing a grain boundary, coming pretty close to a triple junction, and then crossing another boundary, and then heading through another grain pretty uniformly of given crystallographic orientation. And so there's a variation in rate there. There are also fluctuations in here, but these are things we're really interested in trying to understand, and is very much the subject of ongoing current research. But nonetheless, clear-cut differences in rate from these differing crystallographic orientations. With the DIC, forgive me, I don't have time to go into a lot of detail here, but the maps are extracted for surface strains in situ during loading, so we can map out the strains at the unload state, the load state, and everywhere in between, should we wish, and we have all the in-plane components. So here's an example. This is for one of the samples where you get a given strain field. This, I think, is for sample AZ with the large strain magnitudes, and this is for sample BY. So they're very different in qualitative and quantitative nature. We also see, for example, as the crack grows, we see the strain distributions developing ahead of the crack tip. This is always ahead of the crack tip, and they change, of course, as the crack gets longer and the magnitude of plasticity increases. So now we're taking advantage of the cyclic loading in that, and also the knowledge of the strains. So if we make the assumption, which I don't think is too unreasonable, that the DIC strains being total strains, particularly in the unloaded state, are representative of the plastic strain, because in the unloaded state there is no load, it's purely the residual strains plus the plastic strains. We make the assumption that the residual strains are small, so there's an assumption that's the case. But nonetheless, with knowledge of the plastic strains, through the Nye relationship between curvature and GND density, in other words, gradients of plasticity and or elasticity indeed, and G&D density, we can estimate what the G&D densities are from those strains. So this we do numerically from the strains measured from DIC. So we have the plastic strains and we have the G&D densities, in addition to which, because it's cyclic, because at the unload state we have the plastic strains, at the fully loaded state we have the total strains. Again, we can approximate the elastic strain at the peak loading as the difference between the two. And because of that, we can't get this information around every cycle, but we can get that information at the peak of each cycle. So this we do taking full account of all the elastic anisotropy of the crystals through which the crack is growing, and in that way we're able to estimate what the stresses are and the components of stress. And what's interesting immediately is that for sample AZ, which is the more ductile of the samples because of its orientation, the stresses are lower, but they of course increase with progressing crack growth. And the stresses for sample BY, which is more brittle, show higher stresses and of course a higher rate of growth, you may recall from earlier. So we're capturing to some extent the stresses that have been generated at crack tips as they evolve with cyclic loading. And so finally, with all this information of knowledge of the stress at peak loading, the plastic strains, the G&D density, we can calculate then the stored energy density spatially and in particular at the crack tip. And so that's what we're doing, but we convert it to a rate of growth and energy per unit area per cycle. And that's what I'm showing down here for the two differing types of polycrystal where the crack grows through, just snapshots. And we've got the total strain, we've got the stress, we've got the G&D density, and we can estimate what the stored energy density is ahead of the crack tip through the cycles. And I'm now going to summarize that and compare it with the growth data we had before. So this is the experimental data that we discussed earlier, showing the high rate of growth for sample Q, or BY as it's called here, and the lower rate of growth for the more ductile sample, AZ or P. And then I'm plotting the same sort of data on the bottom, except this is for cyclic energy, stored energy density, delta G, plotted up again against effective crack length, same scale as above. And what's very immediately notable is that the stored energy rate for the microstructure BY, in other words, the more brittle or elastically constrained sample, is much higher at the crack tip than that for sample AZ, the more ductile sample, and suggesting that there's a correlation between stored energy at the crack tip and rate of growth, and that the stored energy density is clearly picking up a very strong difference between these differing types of microstructure, or in particular here, orientation, crystallographic orientation, which is driving the cracks at different rates because the stored energy density is different because of those differing crystallographic orientations. And in addition to which, what's quite nice is that the stored energy density also picks up some of the variation we can see here taking place and observed in the crack growth data. And this is something we're very definitely interested in and following up with higher resolution where we can to try and understand more. Okay, let's just relate those to some aspects of the theory that I introduced earlier, the computational approach for modelling the stored energy density at crack tips. So this is the experimental data we've just talked about before. What I'm showing here are crystal plasticity calculations of the two extreme cases where we have single crystal, but we've got this sort of single crystal in one case, there it is. Sorry, that case there is that case there. And we have this case here, single crystal representation, where we've got a single crystal orientated like this. We've got an edge crack, and we're calculating the stored energy density. It's plotted here against path distance away from the crack, so that's at the crack tip. And what we see immediately is that the calculation shows, the crystal plasticity calculation shows that the stored energy density for sample Q is much higher than for sample P. So, and again, the higher value there explains why, I would argue, we see these high rates of growth in sample Q, and it's much lower for sample P, explaining why we see these much lower rates of growth in sample P in the experiments. And just as a comparison out of interest, I'm also showing the dissipated energy, because we can calculate that just as well, which shows as you get close to the crack tip, then of course the dissipated energy tends to rocket up, and it becomes very sensitive on meshing, element size, and all the rest of it, which the stored energy density does not, for reasons I explained earlier. Okay. Also, I can just put into context the results obtained with the non-singular analytical solution I briefly introduced earlier. Here it is again, down here. And so for the two sample types, P and Q, the stored energy from the computational plasticity gives us these two very differing values, as we just looked at for the stored energy at the crack tip. From the non-singular solution, which is simplified, remember, it just has a single slip system, so it's bound to show differences from the computational crystal plasticity, which incorporates all slip systems. We see that it's the same order of magnitude, but more importantly, it's the ratios between one microstructure and the other microstructure are reasonably close. So here are the ratios of the stored energies from the crystal plasticity. We get about 2.35 for the two different microstructures. For the non-singular analytical solution, it's a little bit different, but it's order of magnitude right. And in the experiments, we can look at the ratios of the crack growth rates for the two different microstructures, about 3, and the ratio of the rate of change of the stored energies is 2.5, very close to the the C crystal plasticity calculations, and also not far off from the analytical solution, but also quite close to the experimental observation. So encouragingly indicating that stored energy, both from a theoretical, computational and experimental basis, is telling us that it might be quite good at capturing microstructural sensitivity. So let me move to a couple of examples of application then. First one is a titanium alloy, Ti64, where the sample has been tested independently, published in the literature, showing crack path through the microstructure shown on the bottom left here. So this microstructure has been replicated in the crystal plasticity modelling, and it's shown in outline on the bottom left, the full details up in the model at the top. And we subject it to precisely the same loading defined in the independent paper, and had a look at our predicted crack path, which I will now show you. So this is showing the stored energy distribution as the crack grows, as well as the plastic strain head of the crack tip as it grows, and you can see the rate at which it grows changes, indicating over on the right as well, as this shows, not particularly clear actually, is it, I'm afraid, the crack extension versus cycles. But the key thing is that there are locations where the crack is growing rapidly. There, for example, at the pointer at the beginning and over there, and others where the crack growth rate slows right down, very typical of a short crack growth. So let's have a look at the quantitative comparisons a little bit more. So mostly there's good agreement with the crack path as it grows through the polycrystal. There's a deviation here shown in green, and that happens to be where on the surface of the sample, the tested sample, there's a very identifiable scratch or two, and that deviation of the crack path may be as a result of that scratch. And so we're quite keen to test that out by implementing a scratch in the particular location in our modelling to see whether that solves the difference there. Okay, so just demonstrating the crystallography, the fact that we capture the appropriate grain orientations. There's the experimental observation, calculated observation, with the difference developing on the right-hand side with the experimental polycrystal. One last example is that for zircaloy 4, so the nuclear application, with these two very differing textures, very similar to the ones we've looked at before, but not quite the same examples, where we grow cracks in the lab. In the two cases independently, we nucleate cracks at the notches. So there's the notch in the two cases, and we have a look at the crack paths that are developed, which are shown now. So you can see the two cracks growing. So sample A corresponds to the case where the cracks are growing effectively parallel to the prism systems and parallel to the C-axis, and very largely remain straight. Sample B is the case that's a bit more ductile, where the crack grows on the prism planes, but parallel with the Burgers vector, but at differing rates and different structure of different path developed by the crack as well. Let's have a look at those in a bit more detail. The next slide, where we can see the experimental observation directly and the model in comparison. And here, so the very straight crack for that case, of course, parallel to prism, and down here where the crack clearly oscillates within the single crystal, which is to a large extent what the model is replicating down here, and also the decreasing amplitude of oscillations when the crack gets longer, both in the model and the experiment. So just a few concluding comments. We've hypothesized that stored energy density may be the mechanistic driver of microstructure-sensitive nucleation and fatigue crack growth, short crack growth, and we've tested that against a range of examples, both laboratory and in models. The sorts of approaches are likely to be relevant mostly to safety critical components, where design to ensure safety, of course, is crucial, but unlikely, therefore, to be relevant to all conventional engineering structural integrity, where detailed knowledge of microstructural effects is not necessary. But perhaps most importantly, what is the case is that the state-of-the-art experiments, so from focused iron beam machined micro pillar, micro cantilever, together with nano indentation, the high quality, extraordinary characterization in terms of high resolution EBSD and also DIC and so on, combined with modeling of different scales, are really helping to transform understanding of this long-standing problem in fatigue. Thank you very much for your attention.